This video runs through the first example of hypothesis testing that we did in class today, just so you have a record of it, all written out step by step, and then you can refer to this as we do other problems. We're imagining that we're playing the part of a health researcher who's testing hypothesis about, in the first case, about the percentage of American adults who are smokers. The health researcher wonders if that proportion is the same in her hometown. And so we could pretend like her hometown is Shippensburg and ask the question, is the proportion of Shippensburg adults who smoke also 16.8%? So the first thing to do is document that statement, that that's what we want to test. And so we do that by first making sure the proportion we're defining is clear, proportion of Shippensburg adults who are smokers. And that's a population proportion. There's really no way for us to know exactly what the proportion of Shippensburg adults who are smokers. And so, which is why we're doing hypothesis testing instead of just collecting all the numbers and looking. So our null hypothesis, that's what H0 represents. H0 is what we call the null hypothesis. And that's going to be a statement about what the proportion P is equal to. So in this case, we're wondering whether or not P is equal to 16.8. So the H0 statement will be the equal to case, and we'll always write this as proportions, just so that our formulas and everything work out right. And so if you think about it, if you combine what I wrote in the blank with what I said in part A, P stands for the proportion of Shippensburg adults who are smokers. And so the null hypothesis is the statement that the proportion of, right, this P here, the proportion of Shippensburg adults who are smokers is equal to 0.168. So it's really a sentence. It's not a number. It's a sentence about a population proportion being equal to a number. The alternative hypothesis in this case is going to be just that that's not true. We'll see an example in class on Thursday of where we would have a different alternative hypothesis. But right now, if the researcher is just wondering whether that statement is true or not, then we have our null hypothesis is that the statement is true, and our alternative hypothesis is that it is not equal. And so here we use HA to stand for the alternative hypothesis. Okay, so the way we approach this is we imagine a world in which the null hypothesis is true. And so the main thing about that is I want to draw a picture under the assumption that H0 is true. So this is not something we know. This is something that we are imagining the hypothetical world where this exists. The main implication of the null hypothesis being true is that P is equal to 0.168. And so if I draw the p-hat distribution, this is the thing we talked about last week in class, the p-hat distribution will be centered at the true value of P. So the center of the p-hat distribution is the true value of P, and I am hypothetically assuming that the true value of P is 0.168. Now the other thing we need to be able to label a normal distribution, other than the center, is how big the tick marks are, how far apart they are. That's the standard deviation of this normal distribution. Well, when we're working with sampling distributions, we call the standard deviation, we give it a different name. We call it the standard error. So standard error means the standard deviation of a sampling distribution. So the p-hat distribution is a sampling distribution. So I want to figure out what the standard error is to figure out the standard deviation of this picture. So the formula for standard error, standard deviation of the sampling distribution, is, is this guy. So we're going to take the square root of the true value of P, which again we're supposing is 0.168, times 1 minus P, divided by the sample size. So to be able to draw this, I do need to know what sample size I will be taking in this problem. I don't have to take the sample, I don't have to get the data yet. I don't really need the data until I get down to part G. But I need to know in step C, I need to know how much data I plan to collect. And so I can see from the problem that my plan is to collect 1,100 people, it's a random sample of 1,100 people, and ask them, each one of them, whether they smoke or not. So this calculation, 0.168 times 1 minus 0.168 over 1,100, and then all of that under the square root sign, gives me a value of 0.01127. So I'm going to take lots of decimal places of this. I want to go out much further just to make sure I have that value. If I want to label the p-hat distribution picture that I have here, if I want to label each of these tick marks, I'll round this off to just 0.011. In other words, I'll round it off to 3 decimal places because this only has 3 decimal places. And that's just so I can write this down easily without having to squish my pen too much. So if I add 0.011 to this, I'll have 0.179. And if I add another 0.011 to it, I'll have 0.190. So those are those tick marks. And I won't worry about the third one. I just want to get a couple in here. If I'm subtracting on this side, I'll have 0.157. It's right there. And here I'll have 0.146 here. So I can label a few tick marks in each direction, and I know in my heart that the actual size of those tick marks is this to 4 decimal places. All right, the last piece of bookkeeping that we need before we compare our data is to remind ourselves for this problem, what is the alpha? The alpha is called the significance level. It'll be given to us in the problem. It's right there, 5%. And the way we use that at the end is this is our definition of what small is going to mean in a minute when we need to determine if something is small. So I'm going to write it as a proportion just so it's in the same scale as my other stuff. It's hard to compare when one number is written as a percent and another number is not. So we're going to go all in one way or the other here. So that's my alpha value. Okay, so my part G is to draw a picture of what happens when I really do collect some data. So up until G, I haven't actually thought about what the data says. Oh, I didn't write this in the right place. So this 0.1127 goes here. I didn't mean to fill in the blanks as I went. Okay. So the real p-hat that I have in this problem is 215 out of 1,100. That's what happened when I really did go and ask 1,100 Shippensburg residents or adults whether they were smokers or not. I found out that 215 out of 1,100 were, and on my calculator I can find that as about 0.195. Again, 3 decimal places just because I'm comparing it to this number that's already 3 decimal places. That 0.195, we can see where that fits on our curve, right? That's a p-hat, so it's going to be one of these values. It's going to be about right here. It's bigger than 0.190, but not as big as the next number. So it's going to be right in this area here. If I want to be able to find the p-value in a minute using my table, then I need to convert this to a z-score. So the z-score is going to be that value, the value that I observed, the 0.195, minus the mean, and here I'm looking at this distribution. The mean is 0.168. One of the advantages of drawing the picture is that I have to resolve all of this before I can draw the picture. So the the mean was 0.168. That's what I'm subtracting in the z-score formula. And then I'm dividing by the standard deviation. Remember, the standard deviation is just how far apart the tick marks are. And we figured out up here that was 0.01127. So I put that in my calculator, and I get 2.396. So rounded to 2 decimal places, that's 2.40. On the z-score distribution, the picture, the blank picture I have here, 2.40 is about there. Well, that was drawn pretty badly, actually. About here. Anyway, you know what I'm talking about. So that's my p hat. That's the p hat that was really collected, has that z-score. I shouldn't write equal there. It's not equal. So that's the z-score of my p hat value. So that's a measurement of how unusual the value is. That's pretty unusual. Remember that our empirical rule says that about 95% of all observations are within 2 standard deviations of the mean. And so since this one is outside of that, this one is 2.4 standard deviations from the mean, then it is definitely in the bottom a couple of percent of all possibilities. So it's already, we can already tell it's pretty unusual. The idea of p-value allows us to turn that into an actual probability statement. So to find p-value, all I need to do is shade my picture, and it's hard to even see it. There's so little of it out here. So I'm going to shade on that side, but then also that's how unusual that particular value is. But just as unusual would be things that are over here to the left of negative 2.40. So if I want to write down everybody that is that unusual or worse, I would shade in both sides of this thing. Being unusual in terms of the z-score is just by being a certain distance away from 0. So if you wanted to say who else is that unusual, it could be that unusual and bigger or that unusual and smaller. So it's the difference, like in class, of us saying, you know, whether someone is just has an unusual height would sort of be qualified for both being short or being tall, as opposed to just saying someone is unusually tall or unusually short. So if you said someone's height is unusual, you could mean either short or tall, and we'd want to consider both possibilities. So that's what we're doing here when we do the two-tailed p-value. So to figure out what this is, all I need to do is look up in my table. These two little blue things I've drawn shaded in the picture are identical. So either one of them I can look up. It's smart to always look up the negative one, because the table tells us how much is shaded to the left of whatever we ask it. And in my picture, I want the stuff shaded to the left of negative 2.4. So if I look up negative 2.4, then my table says, that the amount of area is 0.0082. So that's how much area is here, 0.0082, which means that there's also 0.0082 there. And so the total area is the p-value is just the sum of those two things. In other words, twice 0.0082. Oops. Twice 0.0082. So that's 0.0164. So this is my p-value. This is now a probability statement about how unusual my observation is. So a value like that p hat occurs less than 2% of the time. The 0.0164 is 1.6%. So I know that getting a p hat value of 0.195 is among the most rare 1.5% of all the things that could happen. So the question is that a small enough probability that it raises some doubt in our mind? And that's why it was important at the beginning that we decided what a small value was going to be. So we decided up here that for us, small is going to mean 0.05 or smaller. We're going to consider less than 0.05 to be small as a probability. And so notice in this case, that's exactly what happens. So our p-value is small. And when I say that, I mean specifically the p-value I got is less than the alpha that was set for me in the problem. And so that means we believe there's a conflict between the original picture. Here's the picture. This is based on H0 being true. So we started with this picture and we ended up with this probability. So there's a conflict between the original picture and the piece of data that we have. The data and the picture are inconsistent. given this picture, there's less than a 2% chance that we would get this p hat. So we would consider that to mean the p hat and the picture are in conflict. Now, we believe that the data we collected was real from a random sample. So if p hat really happened, then that means we doubt this picture. But that's okay, because remember, this picture is based on an assumption. It's based on the hypothetical assumption that p is equal to 0.168. So we didn't really believe this was true. We just said, well, suppose it is, right? This is hypothetical if this is true. So we have a hypothetical picture and a real piece of data. The two are in conflict, so we say we reject the picture. So the language we use is we reject H0. We reject the null hypothesis. Okay? And so the only other conclusion would be exactly that same thing, but with the word not in it. The only other possibility is that in those two places, we say not. And those are the only two conclusions we'll ever have. Now, when we want to write a real concluding sentence, we want to not have a bunch of statistics jargon about p-values and h-naughts and all kinds of statistics things. So if we reject H0, we say, therefore, we have I'll say significant evidence that, and what I want to write down is, since I'm rejecting H0, I'm going to say that I have significant evidence to support HA. So if I go back up, remember HA means the alternative hypothesis. So rejecting H0 means you believe in the alternative. The alternative is p not equal to 0.168. But I know what p means, right? P is the proportion of Shippensburg adults who are smokers. That's what p is. And the alternative hypothesis says that it's not equal to 0.168. So I'm literally just writing down the statement HA. I'm going to try to write it down in plain language based on the original context of the problem, so that I don't have a bunch of letters and statistics words in it. But this will be my final conclusion, that I have significant evidence that the proportion of Shippensburg adults who are smokers is not 0.168. Again, the only other possible conclusion, if we went back to here and said this was not a small value and we're not rejecting H0, the only thing that means in our conclusion is that we would also have, do not right there. So that you have exactly the conclusion I've written here, or in all three places where I have the red mark, you have do not. If p is not small, we do not reject H0. We do not have significant evidence that HA is true. Those are the only two ways that a hypothesis test can end. Okay, so that's the walkthrough. The assignment I asked people to do for Thursday was to try the problem on the back side of this page. Please go ahead and try to do that. We'll walk through it beginning of class all together, so you're not going to be out on a limb with it, but please give it a shot and see if you can follow this video and figure out all the steps in hypothesis testing on your own, and then we'll go through it on Thursday quickly to make sure everybody feels okay about it.